introduce our next speaker today, Josh Pyser. He's a PhD candidate at the University of Michigan in our chemistry program. So he came to Michigan from Clarkston University. And at Michigan, in his 3.5 years here so far, he's currently a 4th-year student. He's been really interested in thinking about how to apply enzymes in synthesis and how this might be integrated into high-throughput generation of molecules. And so I'll turn it over to Josh for him to tell you more.
Awesome. Thanks, Allison, for that introduction. And thank you all for being here today. I'm really excited to share my work with you on the chemoenzymatic synthesis of Azaphilone natural products. But before I get into that story, I just want to provide a bit of background on the motivation for this work. And so with the ever-growing trend in drug-resistant bacteria and cancers and the need for highly specific small molecule protein inhibitors, it's necessary to sample as much chemical space as possible. And one of the most efficient ways to do this is through high-throughput screening. And so I just wanted to provide a few interesting examples of compounds that were discovered using this technique. So these first two here were discovered through a screen of about 1,000 compounds and were found to be micromolar inhibitors of the novel Zika virus, which cropped up last year. And they represent exciting new drug leads to develop more potent compounds towards this virus. This compound on the bottom left here, ivacaftor, was discovered through a screen of about 230,000 compounds and is used as a CFTR protein potentiator in the treatment of cystic fibrosis. This is a drug currently on the market produced by Vertex Pharmaceuticals and has helped many people around the world. And finally, AzaH, this Azaphilone-based compound, was discovered through a screen of about 6,000 compounds and was shown to have micromolar activity against this HUR mRNA binding interaction. This is a protein RNA interaction that's been linked to the onset of many cancers and represents an exciting drug target in the treatment of these diseases. And so if we think about the way we want to screen as many compounds as possible, we realize that it's also important to develop streamlined synthetic methods in addition to high throughput screening methods. And so if we think about the conventional workflow of taking a compound produced through conventional synthesis and pushing it through to biological screening, we can see that there are a few steps here that could benefit from optimization, especially if you have to go through this workup purification cycle each time you perform a new transformation. And so we propose that biocatalysis has characteristics that will allow us to streamline this process. And specifically, we're interested in developing biocatalytic cascades where you could think about performing a reaction in each well of a 96 well plate, where you could perform multiple transformations at a time and generate a unique compound in each well, and then screen that entire plate directly in a biological assay. And this is made possible by some novel characteristics of biocatalytic reactions, namely that they operate with mild reaction conditions. These enzymes can be highly selective and produce little to no chemical byproducts as a result of these transformations. And their simple workup procedures mean that you can screen the entire reaction mixture directly in a biological assay without interfering with that assay. And one class of compounds we thought would benefit from the intersection of high throughput screening and biocatalytic cascade generation are a class of natural products called Azaphilones. And these are fungal natural products that are characterized by this bicyclic pyranoquinone core and this tetrasubstituted carbon. Some are used in biotech applications currently, but many others have been discovered to exhibit interesting biological activity, such as antifungal, antiviral, and anti-cancer properties. And while these compounds are exciting, they've been underexplored due to the synthetic challenges posed by the construction of this bicyclic core and selectively accessing this stereocenter. Conventionally, these compounds have been made through oxidative dearomatization reactions. So in this reaction, you can start with a planar aromatic compound, typically a phenol, and then through the use of some kind of oxidant, you can dearomatize that ring and introduce your hydroxyl group to give it the desired 3D architecture. Conventionally, metal complexes or hypervalent iodine species have been used to mediate this reaction, but the state-of-the-art in asymmetric oxidative dearomatization was developed by the Porco group, where in 2005, they successfully dearomatized this E9 using a copper oxospartine complex to access this dearomatized intermediate with the R configuration here, and then cyclize that to the desired azaphilone in 84% yield and 99% or 98% EE. And while this represents an important benchmark in the field of azaphilone synthesis, it did require a super stoichiometric amount of this chiral oxidant, which relies on the spartine ligand, which is difficult to come by now. And so fortunately for us, nature has developed efficient methods for performing oxidative dearomatization through the use of a class of compounds called flavin-dependent monooxygenases. And these enzymes work through binding that arene substrate, which triggers a conformational change in the flavin cofactor, which allows it to be reduced by NADPH to give you the reduced flavin. This cofactor then reacts with molecular oxygen to provide an electrophilic source of oxygen to perform that oxidative dearomatization. And then the remaining oxygen atom on your hydroxyflavin is lost as water to complete the catalytic cycle. Now these enzymes have many benefits over the conventional synthetic methods, and namely that for one, it's catalytic, and two, it relies only on molecular oxygen as the terminal oxidant. And so, as I sort of hinted at before, one additional challenge in synthesizing azaphilone natural products is that many of them exhibit the opposite configuration at this C7 stereocenter. And so in order to adapt biocatalytic cascades for the synthesis of azaphilone analogs, we thought a good first hurdle to tackle was to selectively access two azaphilone natural products that had the opposite configuration here. And we envisioned that we could do this through the elaboration of enantiomer-enriched cores, which would have the desired stereocenter preset. And then we could access these two bicycles through the use of two flavin-dependent monooxygenases, which operate with opposite facial selectivity on the same aromatic precursor. And so prior to my work, colleagues of mine had investigated some flavin-dependent monooxygenases like TROP-B and AzaH, which could perform the oxidative dearomatization to give us the R enantiomer, but we didn't have a catalyst that could give us the S bicycle here. And so to uncover this enzyme, we turned to a bioinformatics tool called a sequence similarity network, or an SSN. So Atabay in our lab generated this beautiful SSN here. And this is a tool that allows us to visualize similarities between protein sequences. And so as you can see, all of these dots here are called nodes, and these represent individual protein sequences, and the lines between them are called edges, and these represent a similarity score between the two protein sequences that is above a certain arbitrarily set threshold. And by examining how these protein sequences cluster together, you can make inferences about structure, or you can make inferences about function based on how they cluster together. And so on the left here, you can see this cluster contains AzaH and TROP-B, and so the native products of those enzymes are shown here. And again, these operate to perform the oxidative dearomatization to give the R configuration here. And on the right here, we see a cluster which contains another similar enzyme called SORB-C, which performs a similar dearomatization, but provides the opposite facial selectivity, but operates with a different site selectivity. And so we thought that between these two clusters, we would find enzymes that had the desired site and facial selectivity. And in this bridging cluster in the middle contains a known enzyme called AfoD, which does in fact give us the desired site and stereoselectivity. Closer examination of the biosynthetic pathways of these two enzymes, AfoD and AzaH, reveal that they both operate on a very similar orsanaldehyde scaffold, which is a check in the box for our needs for this project. But just to confirm that these two enzymes do operate with the desired facial selectivities, Dr. Summer Baker-Dockery, formerly of our lab, performed some important seminal experiments where, as you can see in this trace of this chiral separation of this model product made using chemical means, when compared to the same traces from the model product made using AfoD and AzaH, we can see that each enzyme gives almost exclusively either enantiomer of this model bicycle. And so with those two enzymes in hand, we would then wanted to examine or discover a common intermediate that would show activity with both enzymes, but also contained functional handles which we could use for downstream chemistry. So with the help of Summer and Atabey, we synthesized a focus substrate library, which we screened for activity with both AfoD and AzaH. And ultimately, we settled on this enone, as it shows good activity with both enzymes and also contains this internal alkene for downstream chemistry. And so with that common intermediate in hand, we first targeted this natural product called Trichoflectin, which exhibits some interesting antimicrobial and antifungal properties. And so we thought it would be a good first target. Retrosynthetically, we can think about constructing the butynylide ring of this tricycle through an acylation of the C7 hydroxyl and then a subsequent Nova-Nagel condensation onto the C8 carbonyl. As this tricycle was reported to possess the S configuration at the C7 stereocenter, this maps onto the bicycle produced using AzaH in the oxidative dearomatization with our enone substrate. And so I was able to perform a 10 milligram scale biocatalytic reaction, which you can run in just a regular Erlenmeyer flask like this one. And this proceeded in 96% yield and greater than 99% EE to access the desired bicycle. And then I was able to construct the tricycle following this anilation reaction with this acyl ketene precursor, and this provided S-trichoflectin in 99% yield. And so the story takes a bit more of an interesting turn here, in that upon examination of the optical rotation of our synthetically made S-trichoflectin, we found that it was opposite in sign to that which was published for the natural product. Obviously, this had us scratching our heads a bit, and we wanted to rule out the possibility that AzaH maybe operates on the enone with unexpected facial selectivity, or that we somehow inverted the stereocenter during acylation. And so we turned to Dr. Leo Joyce, formerly at Merck, now at Arrowhead Pharmaceuticals, and he was able to calculate a CD spectrum of R trichoflectin, shown in red here, and when compared to the spectrum measured for the synthetically made S-trichoflectin, shown in black, you can see that these are pretty much equal and opposite, which was a good initial indicator that we did have the desired configuration here. But just to be sure, with the help of Dr. Ren Wiskins, formerly of the Matzker group at the University of Michigan, we were able to solve the X-ray crystal structure of S-trichoflectin and confirm that we did have the expected stereocenter. So that being said, we wanted to go back and synthesize the other enantiomer of trichoflectin. And so luckily we had AfoD in hand to access the other enantiomer of that bicycle. Again, I was able to perform this scale up on about a 10 milligram scale. This proceeded in 83% yield and 98% EE. And then following that same acylation Nova-Nagel, I constructed this tricycle, R trichoflectin, and this time, gratifyingly, we see that the sign of the optical rotation matches the published tricycle. And so based on this evidence, we propose a structural revision of the natural product from S to R at the C7 carbon. And so through my work with trichoflectin, we also discovered there was a related series of tricycles called the deflectins, whose absolute configuration was assigned in the same manner as trichoflectin. And based on this, we thought it might be likely that this series was misassigned as well. And so we wanted to synthesize deflectin 1A here. And this time, I used this truncated methyl ketone as our starting material to access this bicycle with AzaH on a 10 milligram scale in 95% yield. And then following that same acylation Nova-Nagel, or a similar one using this acyl ketene precursor, I accessed this tricycle in 87% yield. And after some more help from Dr. Joyce to confirm that we did have the desired stereocenter, this time we see that S deflectin 1A has a positive optical rotation, which conflicts with the original assignment. And so based on this, we propose a structural revision of this series as well. And so with those two compounds in hand, we wanted to go back and synthesize a natural product that should actually come from the AzaH bicycle. And so this time we targeted Lunatoic acid A, which exhibits some similar antifungal properties to Trichoflectin. And so retrosynthetically, we thought we could access this carboxylic acid moiety through an olefin metathesis with our 1,2 disubstituted alkene. To install this chiral aliphatic ester, we thought we could acylate the C7 hydroxyl again, and then use AzaH to set our stereocenter here in the oxidative dearomatization of our enone. So following that biocatalytic scale up, I screened several acylation conditions, which actually proved challenging to acylate this tertiary alcohol. Simple acyl chlorides or symmetric anhydrides didn't seem to be activated enough. And so finally I discovered that Yamaguchi esterification conditions gave us the desired acylated material, this time in 50% yield. And then following that, I installed the masked carboxylic acid as this methyl ester in an olefin metathesis with Grubb's second-gen catalyst and methyl acrylate in 48% yield. And then following saponification conditions with lithium hydroxide, I did observe the mass of the desired natural product by MS. However, due to stability problems, I wasn't able to isolate enough of this compound for NMR studies. But this does parallel instability reported in the original isolation literature, where the authors actually report they methylated the cultural extracts to isolate the methyl ester instead. And so I characterized this compound and found that the sign of the optical rotation this time matches in sign to the original one. And so in this case, we think that the C7 stereocenter was assigned correctly. And so in summary, we were able to achieve the stereodivergent chemoenzymatic synthesis of two azaphilone natural products, Lunatoic acid A and Trichoflectin, through the elaboration of these enantioenriched bicycles, which were generated through two flavin-dependent monooxygenase homologs, which operate on this aromatic precursor with the same site selectivity, but opposite facial selectivity. And so with that work finished, we've begun moving forward towards the use of biocatalytic cascades to rapidly generate tricycle analogs, as there are many literature reports of these types of compounds being biologically active. And so now I've started work on some acyl transferase enzymes which perform that C7 hydroxylation, and then there's a spontaneous Novanagle condensation again to give you the tricycle. And one acyl transferase in particular we're interested in is this one called MR-PIG-D, or as we affectionately call it, Mr. Pig-D, which operates on this bicycle here. And so the idea again here is to generate a number of these tricyclic analogs using Mr. Pig-D and a number of synthetic acyl donors, which acylate a variety of these bicycles, which we envision will be generated in situ using a flavin-dependent monooxygenase like AzaH, which can operate on a variety of these aromatic substrates. And then again, we'd like to take that, run these reactions in a well plate like this and directly screen them in a high throughput screen. And so actually I've had some preliminary success with Mr. Pig-D. Crude cell lysate reactions show that this enzyme does actually exhibit a fair bit of substrate promiscuity in terms of both the azaphilone bicycle and some synthetic acyl donors. So once I get back to the lab, I'm excited to continue exploring the substrate scope of this enzyme. And aside from Mr. Pig-D, we're also interested in generating an entire library of these acyl transferases to access a wider breadth of chemical space. And so I've constructed this SSN of using Mr. Pig-D as the input sequence. And as you can see by playing around with the threshold here, we got a nice cluster is developing around Mr. Pig D, which actually contains some previously characterized enzymes. And so again, once I get back to the lab, I'll be ordering the sequences of these and starting to build up our library here. And so with that, I'd like to thank my lab for all of their help on this. I couldn't have done this without Allison's support and guidance. AzaH was critical in all of the biological experiments and generating the bioinformatics tools. Dr. Summer Baker-Dockery helped me with all of the synthetic work, as well as a previous postdoc. Dr. Megan Hinsey, Dr. Leo Joyce, and Dr. Ren Wiskins were critical in the absolute configuration conundrum. And I'd also like to thank our funding sources from the Life Sciences Institute, the LSA in Chemistry, and the NIH. And I'd like to thank you all so much for listening, and I'd be happy to take any questions at this time.
Thank you very much, Josh. Excellent presentation, very interesting. Again, if you have any questions, could you please use the hand raise feature or chat me just your name so that I know that there's a question, because otherwise it's kind of hard to lose the oversight with so many participants. Josh, if I may start.
Sure.
Do you have any structural information as to how the selectivity is achieved?
Yeah, so we've begun, actually AzaH has collected some crystal structures of a few of these enzymes, and it looks like there are two specific residues in a lot of the active sites of these enzymes that operate through hydrogen bonding. And so by flipping these two residues, you can actually coordinate the aromatic substrate differently. So it's just a simple switch in these two residues, and actually by performing mutagenesis, we can play around with that selectivity.
Thank you. Anthony, you had a question?
Really, yeah, that's really nice talk. Just maybe two very quick questions, if that's okay. So what is it that controls your regioselectivity of your Canova-Nagel reaction? And yeah, maybe the second question is, can you also oxidize the enolic forms of 1,3-diketones, or does it have to be what's it called, phenolic substrates?
Yeah, so to answer your first question, let me go back and pull up this. Let's see. Yeah, so in terms of the regioselectivity for the Nova-Nagel, this was something we thought a lot about as well. And it seems to be that, let's see. It seems to be that something about the internal electronics favors this carbonyl over the other one. So in the biosynthetic pathways of these compounds, there's actually an enzyme that reduces this double bond and changes the internal electronics. And when you do that, you favor the other carbonyl over this one. So that's something we're also interested in playing around with, but that's a really good question. And then, sorry, what was your second question?
Can you also oxidize the enolic form of 1,3-diketones, or does it have to be aromatic phenolic substrates?
For the most part, with these enzymes, they typically operate on these like aromatic substrates, but we are playing around with you know, uncovering like what other types of substrates are accessible here. Yeah.
Okay, thanks very much.
Sure, thanks.
Sabine?
Yeah, great talk. I've got a question. These enzymes, they use these thioesters, isn't it? And can you say a little bit about how available they are? Are they easy to generate?
Yeah, so there are lots of examples of these acyltransferases. So I think, yeah, these here. Yeah, so I've actually worked with a few now. There's lots of them from these Azaphilone pathways. Not too much work has been done with the acyltransferases, but a few have been used to generate some important compounds. I think lovastatin is one, and they've shown that they can actually operate on non-ACP bound thioesters. So they are fairly available, and if we look at this SSN, you can see that there are a lot of protein sequences in this cluster that are very related to the enzymes we're working with. So we're pretty excited about this, and we think that you know, these enzymes should be readily available.
Okay, thanks.
Yeah.
Thank you very much. I'm sure there is an opportunity to reach out to Josh later if there are any additional questions.